Every once in a while, a revolutionary product comes along that changes everything. 100 years ago, the ECG machine was invented. It revolutionized the way we manage heart disease. 50 years ago, the pulse oximeter was invented. It revolutionized the way we manage lung disease. Today, we're introducing an innovative product that will transform the way we manage brain conditions. We're initially going to be focusing on paralysis. This includes conditions such as stroke, trauma, and ALS. As a medical doctor, I've cared extensively for these patients. Their brains are like yours or mine. They can still hear, they can still see, they can still think about controlling their body, but they'll never be able to move their arms or legs. Think of our device as a route to unlocking your brain. It's the size of a grain of rice that we implant to accurately record electrical signals and bypass the site of injury. Not only is the device itself innovative, we've also developed a completely new surgical approach. This involves the use of surgical microrobots that can transport our sensors through the spine to precise regions of the brain in a minimally invasive manner. It's like performing brain surgery without the need to ever cut open the skull. In order to validate the device in vivo studies and demonstrate safety in the implantation process, we require £2.2 million. So thank you very much for listening, and I look forward to speaking to some of you later.
Do you see an investment risk in actually providing two very unique things, which could be together very revolutionary? Is there an approach which allows us to do implant first, microrobots tomorrow?
So I think the most direct route, if you're talking just about the implantation, is to make a hole in the brain, in the skull, and to implant it that way. The way we've looked at designing this is to put the patient at the center of our approach. So when you make a hole, burr hole or a craniotomy, there's a considerable post-op recovery process. We want our patients to have the best recovery process, best surgical process as well. What we found is if we go minimally invasive, we have to look at an alternative route because you can't go through the skull. Going through the spine is a route that is completely novel, and it did require some technological difficulties. But I think if we're putting the patient at the center of our design, we're going to have to meet these challenges, and I think that's what we've done.
Okay.
According to my experience, those brain surgeries are quite expensive, right? You're combining the robots with another very innovative surgery, completely new surgery. Have you considered the cost for patients? Like how are you gonna address that? How much you're gonna sell? Like how are you gonna go through the reimbursement pathway, et cetera, et cetera? Yeah.
So I think the first thing I'd mention is the cost of looking after these patients over their lifetime is about $5.7 million. And that's just the cost itself. Then there's the other factors that you have to consider. The cardiovascular factors that can happen to patients when they can't move their arms or legs. The respiratory factors, the risk of depression, and the list goes on. That means further readmissions into hospitals. They have to constantly be seen by clinicians. They have to be constantly seen in the community. That's expensive. So in terms of our device, yes, brain surgery is expensive. But what we're doing, I think, firstly, is saving cost in the long run. And secondly, it provides an opportunity for these patients to live a normal life. I think putting a price on that is it's priceless for both the patients and the families.
And the device you're describing is both, for want of a kind of use, hard drive sort of terminology. It's both a read and a write. So it's reading what's going on and then actually feeding into action in the brain.
Yes. So we're initially going to be using it for regain of movement.
Yeah.
We're initially targeting the movement of the hand. To do that, we're going to be targeting a particular area of the brain where we pick up electrical signals. So we're targeting the motor cortex of the brain. What we found with studies is if you have a feedback loop, so say you move your hand here, the brain needs to register that the hand is moved. In order to do that, we also have to stimulate parts of the brain. So we're stimulating the sensory cortex. So yes, it has both a read and a write, so to speak.
Not an expert on this. I think some device called DPS. I don't know if there's something related to this kind of device. DPS.
Deep brain stimulation.
Yeah.
So deep brain stimulation is a lot more invasive. So it's targeting a structure that's a lot deeper in the brain. We're targeting more on the surface of the brain. The newer DBS models are sort of closed loop, so they do pick up and stimulate the brain. So I suppose our technology is a sister technology to that device.